So hello everyone, and this is the second session to NMR 2020. Let's go ahead and start with our first presentation with the title Paraconsistent Logics for Knowledge Representation and Reasoning, Advances and Perspectives with Walter Carnielli and Rafael Testa. And I think our speaker is Walter Carnielli. So I'll leave the stage for you. If you can please start, share your screen.
Okay, thank you. Okay, can everyone hear me?
Yes, we can.
Very nice.
Perfect.
So my friends, good morning. It's for me, it's a morning. Nice to meet everyone here. I'll be talking about paraconsistent logic for knowledge representation and reasoning, some advances and perspectives. This is a joint work with Rafael Testa. What I'm going to tell you is how a new logic is not defying, not changing anything from classical logic, but adding some nice power to classical logics. Nowadays, non-classical logics find several applications in reasoning, uncertainty, and managing contradictions and other things like that. Regarding knowledge representation, there is some new views in representing logic of an agent, including fields beyond the AI, like software engineering, database, and robotics. Several logics have been studied for these purposes, including non-monotonic, epistemic, temporal, many-valued, fuzzy logics, etc. So paraconsistent logic is another one. It's not new. It's rather like more than half a century old, but it's not exactly many-valued, nor neither fuzzy, nor non-monotonic, nor epistemic. It's a kind of mixture of everything. More than anything else, it is a extension of a classical logic. So our way of presenting paraconsistent logic is by means of this so-called Lfis, logics of formal inconsistency. They are logics where we add a new connective, a new operator, this white ball here. I hope you see it. This white ball.
Sorry, Walter, you're not sharing the screen.
I'm not sharing the screen? Oh my
No.
goodness. Oh my goodness. I'm sure I am. Let me go back. Oh. Am I now?
Yes, you are. We can see your slides.
Can you see my slides? Oh boy. Then I go very quickly. I go back very quickly. So I talked about the introduction of non-classical logics. And we're now talking about these logics of formal inconsistency, a family of paraconsistent logics where we add a new connective, this white ball, to mean consistency, or something is consistent. Sometimes we also add this black ball to mean that something is inconsistent. So according to paraconsistent logic, there is a distinction between something being contradictory and inconsistent. So contradiction and inconsistent are not exactly the same thing. Contradiction intuitively means that some topic, something is very clearly defined, non-vague, very well put, very well defined, and very well considered. So contradiction is something different. For instance, I may have a different opinion, a sort of a vague opinion about the weather today, if it is hot here in Brazil or not. Some people can say it's okay, well, it's hot for me, not hot for some other people. So this is sort of an inconsistent judgment about the weather. But it's not really contradictory, because the weather, the opinion about the weather is so flexible that contradictions about the weather does not really matter. But if I'm talking about my password, then any contradiction about letters, uppercase, lowercase, blah, 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 can lead to an impossibility of entering a system, for instance. So a contradiction in a password cannot be retained. So the idea of paraconsistent logic is to model this situation according to this principle of the gentle explosion, which says the following. not alpha and alpha by themselves do not lead to any trivialization. But if I have negation of alpha, and alpha is consistent, then I am at the trouble of trivialization. So trivialization is obtained not only by mere contradiction, but it's obtained, trivialization is obtained by contradiction adjoined by consistency. So consistency plus, this is a very important law here, is the only addition that we do to classical logic. So classical logic holds the only thing you have to admit is that the world, the judgments are divided into two categories, the consistent ones and the non-consistent ones. The consistent ones are those guys which are going to produce a triviality explosion and deductive explosion if in contact with contradiction. Okay, that's the only thing you can do. So the hierarchy of Lfis, there are infinitely many different of these logics of informal inconsistency. Some of them are many-valued, some of them are not many-valued. We can have also first-order logics of formal inconsistent, blah, 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 many of them. Just to give you an example, I will be using here, I will be starting from a very basic paraconsistent logic, this MBC, which is just plain classical logics plus just this axiom BC1, which says we express exactly the idea that something inconsistent implying a contradiction implies everything. So all other axioms are classical. I'm just adding this new guy here. And I have to say very clearly that the negation that I'm using here, because I have this law, this last law, is not going to be exactly the classical negation. It's going to be a weaker negation. So just by changing this axiom of classical logic, BC, to BC1, we get a new logic whose connectives are basically classic, except the negation, which is a bit weaker than classical negation because it does not admit a trivialization for any formula, but just for consistent. Okay. So, and the rule of modus ponens, etc. This MBC can be characterized in terms of evaluations, in 0, 1, by evaluations, but it cannot be characterized by finite matrices. This is not any kind of many-valued logic. It can be characterized by valuations which are not classical valuations exactly. They are sort of a semi-classic evaluations in the sense that most properties of valuations hold for them, but the last two, B4 and B5, are only part of the classical valuation. Classical valuations would be if and only if, instead of only one arrow, and B valuation, the B valuation for consistent is 1, not if and only if, but if something is consistent, then or either alpha is false or negation of the alpha is false. So the contrary does not hold. So it's a semi-evaluation, right? So these semi-evaluations are expressed by quasi-matrices, which are distinct to true statements because they expand. In a sense, when I in some points of my table, I get a bifurcation here, and then this gives me a decision procedure, everything like a classical logic, but with a bigger matrix because matrices will be bifurcating at some points. Okay. These quasi-matrices give already give a semantical idea of what the logic does. You see here that, for instance, contradiction alpha and not alpha is not the same as consistency, right? So, or inconsistency. So they differ. So what I can tell you in very quickly is that consistency in this logic is not coincident to non-contradictoriness, and inconsistent is not coincident or equivalent to contradictoriness. So they are different phenomena. Classical logic puts all of them together. Here we are separating these concepts. This is going to be very useful as I will show you. So MBC then separates the notion of consistent and non-contradictoriness in the sense that, see, if something is consistent, then it entails non-contradictoriness. It's non-contradictory, but not the converse. If something is contradictory, it entails non-consistency, but not vice versa, not the converse, right? So they are, these Lfis are at the same time subsystem and extensions of the classical logic. They can be regarded as classical logic extended by two connectives, a paraconsistent negation and a consistent connective. But what's very important here is that I can obtain, I can encode the classical logic within this system. So on one hand, they are classical logic, but on the other hand, they are super classical logic, because classical logic is obtained, is regained inside them. So I have here, for instance, an important theorem, namely the derivability adjustment theorem, which says the following: X in classical logic entails alpha if and only if X plus everything being consistent entails alpha for some system of, for some set of sentences. In this my logic MBC. So MBC goes back to classical logic when I get sufficiently many hypotheses talking about consistency. So what is classical logic in this scenario, in this setting? Is just a logic where everything is taken to be consistent, right? So if you are very stubborn and say that, well, the word is such that everything, every judgment, every statement is consistent, then this logic MBC gives you back classical logic again. So you are not fighting against the classical logic. So there are several other logics, blah, 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 adding sufficiently many axioms, like not the alpha implies alpha, and the converse, alpha implies not the alpha, consistent alpha or alpha contradictory, non-consistency implies, blah, blah, blah. So by adding the converse of these previous axioms, I get lots of interesting extensions of classical logic until I get so many that I'm very close to classical logic. For instance, the logic psi-E or psi, CI, sorry, CIE, CI plus CE, etc. Well, but the important thing here is that I may be adding new axioms that are getting closer and closer and closer to classical logic, but still retaining this paraconsistent character. So these logics have several interesting, in my opinion, in the opinion of my co-author as well, applications in knowledge representation and reasoning. For instance, I can talk about paraconsistent belief change. What is paraconsistent belief change? It's changing your opinions, belief change, where you do not to be so careful about your assumptions. You can retain some kind of contradiction when you are changing your opinion, when you're changing your beliefs. So in Testa, Carnielli, and Ribeiro, they say paraconsistent logics allow the acceptance of the contradictory beliefs, thus admitting defining new operations like external revision, tolerate an intermediate temporary contradictory belief set. So for a certain moment, for a certain time, it's not that we desire to be living with contradictions, but sometimes it happens, and then temporarily we can maintain them and our system is not going to explode. And semi-revision, which is a generalization of the former, in which new pieces of information does not have a priority over the previously accepted one. I mean, I don't need to be very too much careful about priorities or things like that. I can maintain everything temporarily incoherent for a certain time, and then I will be cleaning and working in my belief set and be regaining consistency again. So it's a logic that permits you to be more relaxed about reasoning. That's exactly what human people do. When we find a contradiction in our human way of thinking, we don't explode, we do not say that the word is crazy, but we try to clean, we try to make clear what has been wrong and what is not clear, what has been vague, and let's fix it, and then we get again to a coherent, rational situation. Paraconsistent belief change. Let me give an example to you. A diamond was stolen, only Adam and Bob were present. Okay, there are no proofs, but only evidence. Hercule Poirot cannot consider them guilty. So in his original belief set, he puts, well, it's not, I cannot say it was Adam, I cannot say it was Bob. Adam was not guilty and Bob is not guilty. Okay, later on, the diamond was found in their car, so Poirot belief set now is expanded. Well, I cannot say it was Adam, I cannot say it was Bob, but it was sure one of them. Now, classical logic could not be tolerating this situation. In classical logic, my belief set would be completely trivial, because if it's closed under logical consequence, then everything can be derived from this incoherent, inconsistent, trivial set, right? Because I'm taking this, my belief set is closed under logical consequence. But now, if this logic is not classical, if Poirot, as clearly he is a clever guy, he does not use classical logic. He's going to be used something more subtle, like CIE, one of the closest to classical, paraconsistent logic, very close to classical. In this logic, my belief set does not entail A and does not entail B for a moment. But a new investigation discovered that only Adam used the car since the diamond was stolen. Now, Poirot can assume that the supposition about Bob's innocence is indeed coherent or consistent. I mean, Bob was not the guy, the guilty guy. So he's arriving to a new belief set, K2, which includes now, it's not A, it's not B as before, it was one of them, but the innocence, the presumption of innocence for Bob is really coherent, is really consistent. Now, my new belief set entails that for sure it should be Adam, the guilt. So this K2 also entails that really alpha A and not A was the case. At the first moment, I was not considering Adam guilt, but now I have new evidence, and now the innocence about Adam was inconsistent. I knew that he was inconsistent. It's okay, and I am back to my reasoning. I took a good decision, and I did not go to any explosion, right? So Adam is now proven to be guilty, and the initial supposition about his innocence was proven to be inconsistent. Okay, so I'm really reasoning with negation, contradiction, and inconsistent as different animals here. For what application for a paraconsistent belief change? It gives me a possibility of admitting new and very useful epistemic attitudes. Like, for instance, let K be a given belief set, then I have the following categories. A sentence is accepted, it belongs to K, is rejected if its negation belongs to K, is underdeterminate if neither alpha nor negation of alpha belongs to K, is overdeterminate if both belong to K, and I don't get an explosion because of that, is consistent if it consistent of alpha belongs to K, is boldly accepted if consistent of alpha is in K and alpha as well is in K, boldly rejected if consistent belongs to K, a negation of alpha belongs to K, that means not G in a certain case does not belong to K. But anyway, well, this gives me a new sort of lattice of epistemic attitudes. The arrows here, this line here are hold for exclusion, for inclusion, set inclusion. And then they are new epistemic attitudes in what we call AGM ball. I mean, it's an expansion of the AGM paradigm, where I am dealing with a new, as I call it, reasoning tool. I have a new reasoning tool at my disposal, right? So
I just want to turn your attention that you have 2 more minutes.
How many minutes do I have?
2 more minutes to allow for questions.
Okay, so I'm going to skip this example adapted from Hamilton here, which just shows how I can accept very entrenched beliefs, and I can handle them with this new logic, and go to probability reasoning very quickly. Probability can be regarded as degrees of belief that a rational agent attaches to events. So paraconsistent probabilities can attach rational degree to agents even if degrees of belief might be contradictory, right? That it's not impossible for an agent to believe the proposition alpha and not alpha, and to be completely rational if his belief is justified by evidence. So that's one. I'm going to skip this slide as well. This shows only how we can attach probabilities to non-classical logics in general by a way, formal way to attach probability to a consequence operation. I go very quickly to an example. By attaching probability to this logic, we gain a new form of Bayes conditionalization, Bayes theorem, Bayes conditionalization rule, where it's exactly the same as the old one, but we exclude a little bit of our contradictory thing. So I just to tell you in 1 minute, I will be sort of reasoning with Bayes conditionalization as I do in classical logic, but I have to be aware that I may have some entanglement between alpha and not alpha. And this entanglement can be measured. They will have a degree, and they will have also a probability. I have to take into account this entanglement. And I can say, sorry, again, how much time I have?
1 more minute.
1 more minute. So in 1 more minute, I cannot give you any very sound reasoning here or very sound calculation, but I tell you the following: we can, for instance, use this kind of setting for instance, spam, where I have, for instance, I have one source gives me that I have 30% of probability that given me is spam, and the other one gives me 85% that is not spam, that is ham. Of course, I will have like a 15% of coincidence between spam and not spam. So I have a contradiction, a part of a contradictory thing here. I can measure it. I can reason with this new information here. I can apply Bayes' theorem to this kind of reasoning. And what I get here is very interesting. I have a different way, like using paraconsistent probability, we get a new way of computing the probability that some thing is a spam, giving some certain characteristics like suspicious characteristics. Using paraconsistent logic, I obtain there's a probability, even if there is a contradiction on the definitions here, I can compute that this probability is not any crazy thing, but is 61%, and compare them to the classical cases like cleaning before the contradiction, and I get 65, 56, 44, blah, blah, blah. What is important here is that I really gain a new result, a new tool, reasoning tool, as I call it. Then I can really make up a clear and sound computation using paraconsistent probabilities. Other applications, I can apply them, of course, to description logics. I can apply them to notion of evidence, to Bayesian networks. That's one thing where we are working at the moment. I have a PhD student working on the possibility of creating and defining paraconsistent Bayesian networks, I mean, mixing probability and networks under this new logic. And what I can say for you is that these paraconsistent logics can really expand our arsenal of reasoning tools. And we have no reason not for using them. If they are very rational, and they sort of describe very close the way of where we human people reason, right? That's very important for me. So reasoning somehow is more important than logic. I think that anything that can happen, reasoning to happen, is very welcome and is a nice tool into our arsenal of rationality. Thank you. I'm ready for questions.
Thank you very much for your interesting talk. Are there any questions?
Well, I'm glad there's no questions. I mean, people maybe they are shocked, or maybe I did not explain it well, but anyway.
So there does not seem to be any questions. Let me thank the speaker once more. Thank you very much.
Thank you. I thank you for the attention. Thank you.
Let me move ahead to the second presentation of today. So our next talk is titled BKLM, an expressive logic for defeasible reasoning, for Giovanni Casini, Thomas Meyer, and Guy Paterson-Jones. I think our speaker is Guy Paterson-Jones. If you can please start sharing the screen.
All right, let's see if I can get this to work. Can you see the screen and hear me?
Yes, we can. Please go ahead.
Okay. All right. So, hi, everyone. New on the scene here. My name's Guy. I'm a master's student at the University of Cape Town under Giovanni Casini and Thomas Meyer. And yeah, today my goal is quite modest. So I just want to tell you about some interesting things that happen when you extend the syntax of the KLM framework for feasible reasoning. Yeah. Oh yeah. Sorry, having issues moving my slides. Ah, there we go. Sorry, I'm having some technical issues here. All right. Okay, so I'll start with a background on what the KLM framework is, although I'm sure that'll be quite familiar to everyone here, just for completeness. So about 30 odd years ago, Krauss, Lemon, and Magador wrote two, what comes to mean as a KLM framework for non-monotonic reasoning, in which they take propositional logic and extend it with this twiddle symbol. And the way one reads these kinds of formulas is alpha typically implies beta. And so their goal is to provide a logic to reason about generic properties in the face of exceptions, which is something that, as we know, classical logic can't handle too well. When you have exceptions, then you get this explosion, as Walter mentioned in the last talk. So in these papers, Lemon and Magador consider a number of properties that non-monotonic reasoning we should expect it to hold, to have. And these are all quite standard and well known in the literature, so I won't spend too much time going over these. But just for some examples, here we have the AND rule, or conjunction in the conclusion, which says that if we expect beta to follow from alpha, when all things being equal, and we expect gamma to follow from alpha, then it stands to reason that we should expect beta and gamma to follow from alpha. So that's quite intuitive and easy to motivate. So one of the more interesting properties in their framework is this last one, rational monotonicity, which, as it's written here, is a little bit tricky to understand, but it says that if you expect gamma to typically follow from alpha, so in the most normal situations where alpha holds, we expect gamma to hold, then you should really conclude, you should really expect gamma to follow from alpha and beta unless you have reasons to believe otherwise. And in the case of rational monotonicity, the reason to believe otherwise would be, for instance, if not beta typically follows from alpha. Because in that case, then alpha and beta would be atypical, and so we shouldn't really make any feasible conclusions from it. So in the KLM framework, semantics is given by a preference structure. So you take every propositional valuation or possible world, and you assign it a rank, which represents how typical that valuation should be considered. So quite standard example would be this one here, where we have three propositional atoms, P, B, and F, representing being a penguin, being a bird, and flying, effectively. So, in this case, the valuation in which penguin, bird, and fly are all true would be quite atypical because it has rank 2, whereas the valuations at the bottom would be considered very typical. So given such a structure and some conditional, such as not F typically follows from P, to see whether it's true, we take all the valuations in which the premise holds. So in this case, it would just be the two highlighted valuations. Then we take the most typical of these valuations and we check whether the conclusion holds. So in this case, the most typical world in which penguin is true is this guy here. And in that world, not fly holds, so this conditional holds. And one of the many interesting things that Krauss, Lemon, and Magador prove in their papers is that these ranked interpretations completely characterize rational KLM style knowledge bases. So whenever you have a set of KLM conditionals that satisfy the properties I showed on the previous slide, then you can find a ranked interpretation that has exactly those conditionals as its set of true formulas. So that's all quite nice, and that's sort of a starting off point here. So the next question is, given some partial knowledge base, how do you sensibly extend it to a rational knowledge base? Because typically we don't carry around complete rational sets of knowledge in our minds. And there are a number of answers to this question. In the Lemon and Magador paper, what does a conditional knowledge base entail? They present rational closure, which is a very well known mechanism for this. And rational closure can be viewed as a kind of minimal model semantics. You take the most, you try and push down the rank of valuations as much as possible with respect to your knowledge base. And this gives you the rational closure of your knowledge base. It has some issues, such as so-called drowning effect. If a class is exceptional in some respect, so penguins, for instance, are exceptional birds because they don't fly, then in the rational closure, penguins don't inherit any typical properties that birds have. So for instance, we could not conclude that penguins fly, we wouldn't conclude that penguins build nests, etc. But there are ways around this. So Lemon, in a 1995 paper, defines lexicographic closure, which satisfies this principle. Relevant closure more recently by Casini et al. Is another kind of closure that does this. But general consensus seems to be that interesting forms of entailment for KLM knowledge bases should extend rational closure. So rational closure is kind of our lower bound for what we want in an entailment. And that's kind of the kicking off point for us in this paper. Right, so what extensions of this original framework, KLM, have actually been considered so far, and what's the issue here? Well, the problem we look at is it's not very expressive. You can express positive conditionals, such as beta typically follows from alpha, but you can't do a number of other things that might be considered useful. So you don't have negative conditionals. You can't say stuff like beta doesn't typically follow from alpha. You can't take conjunctions or disjunctions of these conditionals, and you certainly can't nest these conditionals. So all of these red highlighted formulas are just invalid syntactically in the KLM framework. Of course, as soon as you add stuff like this and make it more expressive syntactically, it becomes more expressive semantically. And as a result, entailment becomes harder to define. This is, of course. So the question for us really is, can we still define analogs of rational closure, or what are the reasonable non-monotonic forms of entailment for these extensions? So one of the earlier extensions was a paper by Booth and Paris in 1998, and they consider KLM where you can have both positive conditionals and negative conditionals. So it's one small step towards a more expressive logic. And this introduces some minor issues like consistency. For any KLM knowledge base, there's always at least one ranked interpretation satisfying it. But in this extension, that's not necessarily the case because, for instance, no ranked interpretation can satisfy beta typically follows from alpha and beta doesn't typically follow from alpha. It has to pick one or the other. So there are some knowledge bases that don't have any models whatsoever, but that's not really a big problem. And in this paper, Booth and Parrish show that any consistent knowledge base has a rational closure. They give a semantic characterization of rational closure in terms of this kind of minimal model idea, and they show that even with negative conditionals, there's always a unique minimal model. And when you restrict to the positive conditional case, it's exactly the rational closure as Lemon and Magador defined it. So that's quite encouraging. Somewhat later, another logic that can be considered an extension in some sense of this framework is propositional typicality logic, which I think was proposed by Booth et al. In 2012 first. So I've actually lied a bit here on this slide. And the way this works is it does something a bit different. Rather than considering literal extensions of KLM with this twiddle connective, they consider propositional logic extended with a modal typicality operator. So this typicality operator can be put anywhere in a formula and can enclose arbitrary propositional formulas, can be nested. And one reads this as typical alphas are typical betas. So this bullet symbol really means that it really represents typicality. So this is clearly more expressive than KLM in at least one respect. In KLM, typicality only refers to the premise of your conditionals, whereas in PCL, you can express typicality anywhere, and in any form you like. You can use disjunctions, implications, etc. So it's quite a lot more expressive. However, it turns out that when you extend KLM with this level of expressivity, you start to lose some desirable properties of your non-monotonic entailment relations. So in this paper, it's shown that sort of minimal model semantics in the spirit of rational closure can still be defined. I think they call it LM entailments in the paper. But some bad things happen. When you take the rational closure of a PCL knowledge base, you can end up with classical assertions in your knowledge base, or classical assertions in the rational closure that weren't present in the original knowledge base. So you start to get feasible information effects on classical information, and this might not be desirable. Right. So what did we do in our paper or notes? Well, we took it a step further and we said, right, so let's consider KLM where you can have arbitrary Boolean combinations of conditionals. So still no nesting, but you're allowed to have disjunctions, conjunctions, negative conditionals, etc. And we use the same semantics as the original KLM framework. So ranked interpretations are what we're interested in. And it's clear that this is more expressive than KLM. What was a bit more surprising to us was that it's also more expressive than PCL for ranked interpretations. And there's at least one way to see this. So an analogy to propositional logic here, as everyone knows, for any valuation in propositional logic, there's a formula that has that valuation as its unique model, the characteristic formula. And that's easy enough to see. And for BKLM, a similar thing happens. Given any ranked interpretation, or actually any subset of ranked interpretations, there's a formula that precisely characterizes that subset. So in some sense, for ranked interpretations, this Boolean KLM extension is maximally expressive. And the same is not true for propositional typicality logic. As shown in the 2012 paper by Booth et al., there are sets of ranks and separations that cannot be characterized by any PCL knowledge base. So at least in principle, BKLM is more expressive, but it's not very satisfying because it doesn't tell us how or why it's more expressive than PCL. So one of the results in our paper is showing that there's a direct translation of PCL knowledge bases into Boolean KLM knowledge base, such that the set of models is exactly the same for both. And I won't go into the details of what exactly is going on here, just in the interest of time. But essentially, for any world in the ranks and separatation U, we define a translation operator that encodes truth of PCL formulas with respect to that valuation U. And then by taking an appropriate conjunction of these translation operators, we can encode PCL knowledge bases directly. So the other question is then, can we do the same thing we did for PCL and the earlier extension of KLM? Can we define analogs of rational closure? Or in other words, do these minimal model semantics work nicely for Boolean KLM? And unfortunately, it turns out they don't. And we actually prove an impossibility theorem of sorts, saying that a number of quite nice properties you'd want for defeasible entailment for BKLM can't all hold simultaneously. So as far as rational closure goes, a sort of key property is the single model property. And this is something that rational closure for PCL, KLM with negation, all have. And that's that given any consistent knowledge base, you want your set of entailments to be characterized by a single ranks model or ranks interpretation. Or put differently, single model property says that your entailment produces a rational set of conditionals as a consequence. And it turns out that if you insist on this for Boolean KLM entailments, then the resulting entailment relation has some very bad properties. It is possible to define such entailments, but as we show in the paper, they are undesirable. They correspond to an a priori choice of total order over the set of all ranks interpretations. And so that's no good. So for feasible entailment, one would have to look elsewhere for BKLM. Right, that's all I wanted to say today. Hopefully I haven't used too little time. But essentially what we did is considered some extensions of the KLM framework. We looked at feasible entailment for them, and we found that in the case of Boolean KLM, a lot of nice properties we'd like to have actually cannot be defined at all. So, and we provided some translations of the previous extensions into Boolean KLM. Yeah, that's me. Are there any questions about this?
Thank you very much for your talk. Are there any questions? So let me thank our speaker. And this is time to move ahead to our last talk for today. Our title is a framework for modular multi-concept lexicographic closure semantics for Laura Giordano and Daniele Theseider Dupre. If you can please start your presentation, please go ahead.
Thank you. This work, I have to, okay. The aim of this work is to define multi-concept lexicographic closure semantics for a modular defeasible description logic. So the idea is that the context is the same as described in the previous paper, where we have defeasible properties expressed like typicality inclusions. And the idea is that we want to build modules where by distributing defeasible inclusion in these modules, and each module has its subject concept. And the idea is that we will define a a preferential lexicographic closure semantics by associated with each module a preference relation. So we define a multi-preferential semantics, and we will combine all the multiple preferences into a single preference to define the meaning of the typicality operator. So our language will have just one typicality operator, but many preference relations. And the motivations is that this kind of semantics, we want to go towards a framework for defining different semantics, a sort of spectrum of different alternative semantics, including existing ones. And according to the granularity of the modularization, whether the module contains all conditional or just one conditional or just a conditional for a given concept, according to the choice of the semantics for modules, and which must be a ranked semantics, but we have chosen here the lexicographic one, but other can be adopted and have been adopted in other works. And finally, according to the multiple preferences combination, we get different semantics, and we will consider some interesting ones. And the aim is to define the notion of conditional entailment, satisfying the KLM properties of preferential relations, which is not a notion of entailment, which is not subject to the blockage of property inheritance. So we can inherit properties unless there are exceptions, and there is a form of overriding. Of course, we want to deal with specificity and the irrelevance, but also to avoid some problem of the rational closure, that is not only the blockage of property inheritance, which is a problem of rational closure, but also the fact that sometimes rational closure is too strong. So in some cases it is too weak because there is not enough inheritance does not work, and in some cases it's too strong. And the problem was already pointed out by Geffner and Pearl in '92, that sometimes rational closure and system Z, which is equivalent, solve conflict in an anomalous way, conflicts which should remain unresolved. We will come back to this. So our language, the language we consider is the description logic ALC, and we will just use I will not enter in the detail because I will just use intersection, union, and complement of concepts. So we have concept inclusion, all C's are these, all mothers of a doctor are individuals which have at least a child who is a doctor. We have assertions, Mary is a female, Mary has Carlo as a friend, and the interpretation of concept names is a set of domain individuals. So interpretation are sets of individuals and an interpretation function. The interpretation function associates to concepts names a set of individuals, to relation as a binary relation over the domain, and to individuals an element of the domain. And the interpretation of the intersection, union, and complement is the theoretic one, essentially. So what we consider is an extended language in which, as it was already explained before, we have sort of conditional assertions that we represent as typicality inclusions. And for this kind of logic have been considered a preferential semantics, but also a rational one, a rational semantics. And in this work, we will consider both of them. We will need both of them. So I shortly recall the meaning of what is a preferential semantics for ALC. So in addition to the domain delta and to the interpretation function we have seen before, we have a preference relation among individuals. X is less than Y means that X is preferred to Y. It is more normal than while, it is less abnormal, it is more typical than while. And the set of typical elements, the typical C elements, is represented, consists in the set of minimal instances of C with respect to the preference relations. And if we add modularity to this, to the definition of the preference relation is a partial order, and it is also well-founded. So there are not infinite descending chains. If we add the modularity condition, we get a ranked interpretation where each element of the domain can be given a rank, 0, 1, 2, and so on. For finite knowledge bases, we have a finite number of ranks. And from this notion of preferential and ranked interpretation, we get, in a natural way, a notion of preferential entailment and rational entailment, like in the propositional case, in KLM case. And as these notions are very weak notion of inference, by minimization, one gets, considering just minimal models, and in particular minimal canonical models, this model must contain, must have a domain enough large, essentially. Well, this kind of models are the models of the rational closure. I will not define the rational closure, but just recall what is the rational closure ranking. The rational closure ranking assigns a rank to all symbols, to all concepts, and to all concept inclusions. A concept as low rank is if the concept is not exceptional. So suppose that student has rank 0 because it's not exceptional. The concept PhD student may have rank 1 because typical PhD students have scholarship, while typical students do not have. And we know, this is a strict inclusion, that PhD students are students. So PhD students are exceptional students. Employed students are exceptional employees. Employed students on holidays are exceptional employed students. So we have a ranking of concept as well as concept inclusion. This notion of ranking is used to define the lexicographic closure and its semantics. And well, so here I have already told that what I want to avoid and to get with our approach to avoiding too weak inference, but also too strong, and to represent the fact that we might have different preferences with respect to different aspects. That is, Bob can be less preferred as a student than Tom, but Tom may be, Bob can be more preferred as a student than Tom, but Tom, vice versa, can be more preferred as an employee. So we go to consider a preferential semantics in which we have multiple preferences. And here, the problem of having multiple preferences has been considered. And for instance, in the circumscription, in circumscripting knowledge bases, with an abnormality predicate depending on the proposition, by Fernandez Gil, considering typicality operators which are associated to different set of clauses, set of defeasible inclusion. But well, here we will consider just one typicality operator, and Yotzi also is considered a multi-preference interpretation, notion of multi-preference interpretation in which preferences are associated with different aspects, but this is a refinement of rational closure. We don't want to get a refinement of rational closure because we want to avoid the too strong inferences of rational closure. That from the point of view of syntax, our knowledge bases are contain a set of strict typicality inclusion concept inclusion, a set of defeasible inclusion, which are distributed in a set of modules M1, M2, MK. Each module has a concept, which is the subject of the module. And this is an example. Module 1 contains the typicality inclusions for student, PhD student and employees, and so on. The subject is student. Module 2 has subject employee and contains all the properties of employees and subclasses. So also employee student. Employee students, the properties are in both modules, for instance. The idea is that to give the meaning of this program, one associates to each module a lexicographic interpretation by means of a preference interpretation, a preference relation. The kind of construction will be similar to the one by Lehmann in propositional lexicographic semantics. We want just to mention that there is, of course, another option to have big modules like student containing all student information and rules about students and their subclasses. We might have small modules, each one associated to one concept. So a module for student, a module for PhD student, a module for employee, a module for employee student, and so on. This option has been considered in a companion paper in IC that will be presented in ICLP 2020 next week. And in that case, we associate for a given concept, let's say student, a rank to each inclusion, typicality inclusion, and build the preference from this rank. So here we follow a different pattern, and we use lexicographic closure. I recall Lehmann lexicographic closure shortly. And so in Lehmann semantics, the preference among two words is defined using a notion of seriousness ordering. That is, W is preferred, is a word as a propositional interpretation, is preferred to W prime if the defaults violated by W are less serious than the default violated by W prime. What means less serious? Less serious. Violating a more default with higher rank is more serious than violating a default with lower rank. Violating more defaults is more serious of the same rank, is more serious than violating less. So both criteria are considered. I will not enter in the definition for time constraints, but the idea is that the same definition of lexicographic semantics is transposed to the ALC case, but the preference relation is defined on the domain delta. So here X and Y are domain elements, and I consider violations, the set of defaults violated by a domain element. If the set of defaults violated by X is less serious than the set of default violated by Y, then X is preferred to Y. So this is the preference relation is inside the module, exactly like Christophe Ransaudis told about his approach. But as we consider modules, we project the knowledge base on the single modules, and we define the knowledge base Ki associated with module I, with the strict part of the knowledge base is the same for all Ki, but the defaults are the defaults of module I for each I. And when I define a preference relation for each module, X is preferred to Y with respect to module I if the violations of X concerning module I are less serious than the violation of Y concerning module I. So I take the same definition as before, but projected over the single module. So in this way, I associate a preference relation to each module. And now I can put them together. So let us consider we consider a multi-concept lexicographic model where we have the delta and the interpretation I determine a model as usual in ALC, a model of the strict part of the knowledge base. And the preference relations, less 1, less 2, less k, are the relations associated with the different modules. And what we are interested in are the canonical multi-concept lexicographic modules, that is, those models in which delta is enough large. We need enough individuals to define a model. This is the same as in the as in the rational closure interpretations. So, given this kind of multi-concept lexicographic models, can we evaluate all queries? If we want to ask about typical properties of students, well, we can use the module of students. The same for PhD students. So we will use module 2. But what about if we want to know the typical properties of employed student? This is concerned with employee and with student. So with both modules, M1 and M2. This, to address this kind of question, requires the combination of the preference relations. And so the idea is to define, as we have a single typicality operator, the idea is to define a notion of global preference. And as in this case, the lexicographic closure also already deals with the specificity inside the single modules. So the preference relation for the modules already deal with the specificity inside the module. Here we have considered a global preference relation, which is just a Pareto combination of the preferences 1, 2, and k. So x is preferred to y if for some module I, x is preferred to y with respect to this module. And it is not vice versa for all other modules. So for all other modules, it is not the case that y is preferred to x. The resulting relation is a partial order relation, but in general it is not modular. So this does not give a ranked interpretation. This notion of global preference, so we can define using this notion of global preference, what we have called a combined lexicographic model, delta, the global preference, and the interpretation. This notion of interpretation is indeed a preferential interpretation in the standard sense, as we have recalled before. It satisfies, a combined lexicographic model satisfies all strict inclusion and assertion in the knowledge base, but the preference relation, which is obtained by combination of the multi-preferences as defined by the lexicographic closure, is not required to satisfy all typicality inclusions in the knowledge base. So what does it mean? It means that this semantics is more liberal with respect to the standard preferential semantics. In that, for instance, in this example, we have the typical student are young person, typical young person are student. These two assertions together giving the preferential semantic, the typical student coincide with typical young person. And so it is not possible, it is not consistent, that typical students are quiet and typical young person are not quiet. This set of clauses of definition, this set of inclusion has no model, no preferential model. Instead, it has a combined lexicographic model. We may have that Bob is a typical student and is preferred with respect to relation less 1, and John is a typical young person and is preferred to less 2, but the two are not comparable, as Bob is preferred to John with respect to relation 1 and vice versa. So globally, they are not comparable, and both of them will be in the minimal set of students with respect to the preference relation. This
Just a
notion
reminder, 1 more minute. You have 1 more minute.
Okay, that's perfect. So with this notion of model, we define a notion of entailment. The notion of entailment can be seen that the notion of entailment satisfies the KLM properties of a preferential consequence relations, avoid the Ronen problem, so it allows inheritance, and as we have seen, and avoids unwanted conclusion of rational closure and also its refinement if proper modularization is chosen. And in particular, essentially, the idea is to separate in different modules concepts that are not related, for instance, Italians and PhD students, because otherwise I will compare the rank of PhD students with the rank of Italians, and they are clearly, PhD students are not clearly a more specific concept than Italian. But in the rational closure and in its refinement, I consider that the rank of PhD student, suppose that it is 1, is more than the rank of Italian in this example, and this makes me to conclude that if typical Italian are owner and typical PhD student are not owner, I would like not to conclude anything about typical Italian PhD student, but I go to conclude that typical Italian PhD students are not owner in the rational closure and in its refinement. A hierarchy of module we have not considered in detail in the paper, but we are given some hints, can be defined by considering the specificity among concepts, and this leads to a different notion of combination, which needs to deal with this specificity outside the module essentially, and this has been addressed in the paper I mentioned at ICLP 2020. To conclude, there are several related work dealing with preferences. The work by Liozzi, which is defines a semantic which is stronger, it is a refinement of rational closure. The work by Gill, who defines logic with multiple typicality operator. We have just one, so this logic does not deal with combination of preferences. The work by Britz and Barczyk dealing with defeasible role quantifiers and defeasible role inclusion. We don't have addressed this problem of having defeasible roles in this paper. The work by Kernes, Berner, and Ritter-Scamp in the propositional case, which also this work also deals with the preference, preference combination called preference fusion, and exploit the rational closure partition to combine the different preference relation, one for each rank, with giving preference to the higher rank. There is some relation also with contextualized knowledge repositories, which deals also with modularization of description logics and low complexity description logic, and ASP-based reasoning has been used for that. And the paper I mentioned also at ICLP also deals with ASP, also address the problem of reasoning through ASP and preference relation. The plausibility of this kind of preferences associated with concepts has been studied using this kind of semantics for defining a logical interpretation of self-organizing maps, which are psychologically and biologically plausible neural networks introduced by Cohen. So as future work, we would like to explore further this correspondence, and especially to see if from the practical point of view, this looking at self-organizing maps as multi-preference interpretation and validating on this interpretation conditional formulas by model checking essentially is feasible in practice. Thank you.